Hello, and thank you for your interest and time today. I am David Massey, Vice President Business Development with MaXentric Technologies. I have over 37 years of experience developing advanced RF technologies for the DoD in commercial markets. Today, I will review our Navy Phase 2 SBIR project, Dynamic Airborne Radios for Wideband Interoperable Networks, or as we call it, DARWIN, and talk about its benefits for the Navy and where we are with the development of the technology for future ship and battle group communication systems. But first, an overview of MaXentric Technologies. MaXentric Technologies is a small business with a focus on advanced RF technologies, research, and product development. We focus on technologies and products for the next generation of advanced communications and radar systems for mobile platforms. We have offices and laboratory space in La Jolla, California, and Fort Lee, New Jersey, and we are opening a new office in Boulder, Colorado in the June 2021 timeframe. We currently have staff of over 50 engineers with about 20% of our staff at the PhD level, focusing on both military and commercial customers. Our client base includes commercial customers such as Verizon, Sprint, Cablevision, SiriusXM, and Airbus, and our government customer base includes DARPA, NASA, MDA, Air Force, Army, Navy, and DHS. In wireless systems, we are developing next-generation wireless technologies to introduce capabilities and enhance proficiencies, particularly in the microwave and millimeter wave bands. Our product areas include ad hoc wireless networks for airborne communication platforms, high-resolution imaging radar, software-defined radios, simultaneous transmit and receive systems, and LPI, LPD radar and communication systems. Our RF and digital signal processing platforms include mixed processor systems for improved performance and design flexibility. These systems include FPGAs, mini-core GPU, CPUs, digital beamforming, RF SOCs for radar and communication systems. MaXentric also develops custom ASICs for RF systems, including linearization and digital pre-distortion for improved amplifier efficiency, as well as custom 5G RF SOC solutions for miniature data links, including Type 1 encryption for handheld radios in Army Group 1 and larger UAV platforms where SWaP-C is critical to mission success. Finally, and for the topic today, MaXentric is a world-class leader in the design of millimeter wave communication systems for satellite and mobile communication systems. DARWIN was released as an SBIR topic in 2018 to develop and demonstrate a modern, over-the-horizon, military resilient communication ISR network, but with the capabilities that commercial 5G networks would offer. DARWIN addresses the joint service wireless high data rate and tactical network communications, interoperability, and targeting gaps for all the DoD services, Coast Guard, Border Patrol, COCOMs, and coalition forces, enabling the Joint Chiefs of Staff, Joint Communications, interoperability vision. Manned and unmanned air vehicles as nodes could increase their utility to the fleet by operating as an airborne network. Current bandwidth efficient data links, BE-CDL, antennas availability, and positioning on the airframes often don't allow for anything other than omnidirectional communications. But with directional antennas, simultaneous multi-channel communications could be enabled. This enabler would support full two-way communications with multiple nodes for transfer and relay of high data rate, imagery, command and control with 360-degree coverage and expanded air tier slant ranges. A millimeter wave high-capacity backbone can provide long-range relay extension in SATCOM-denied environment and act as a 5G backhaul capability. Current CDL antenna technologies, such as gimbal dishes, do not support simultaneous multi-channel communications capability. CDL omnidirectional antennas could support the multi-channel capability, but they lack the gain in the multi-channel bidirectional communications capability needed for the DARWIN program. The CDL directional antennas also don't support the high-speed multi-point distribution needed in a networking environment. Several possible solutions have been ground tested for other situations outside of the Navy, including multi-beam antennas and phased array antennas, but with limited success, and not the ability to be able to be scaled to airborne platforms. Significant issues with size, weight, and power must be overcome to make any solution viable for legacy airborne platforms in small classes of UAVs. So DARWIN hardware to date has developed a low swap, high data capacity RF modem radio system using spectral, agile, multi-channel, multi-band, wideband software-defined modems and transceivers to establish a multi-communication links using segregated and scattered frequency bands in spectrum challenge environments. At W-band, we've developed a 94 gigahertz full duplex front end that has a 1 gigabit per second modem, which can be reprogrammed for different modes of operation and modulation schemes. At X-band and KU-band, we've developed and demonstrated adaptive digital beamforming that supports bandwidth efficient CDL channels. It's based on an RF SOC system that has very low latency, and the adaptive digital beamforming firmware can identify nodes within the digital beamforming field of view within a very short amount of time. We offer 8 to 16 full duplex independent communication channels, each supporting about a gigahertz of instantaneous bandwidth in a full duplex mode with spectrum agility across all the available apertures and antenna systems that are connected to it. We offer digital signal processing hardware to handle implementation of the complex modems and waveforms. The wideband waveforms are designed for LPD, LPI, and LPE and support communication links with throughputs ranging anywhere from 10 megabits up to 1 gigabit per second. The system is software defined, and the hardware is agile and allows maximum flexibility for additional waveform implementations. We offer 8 to 16 channels of coherent digital beamforming and beam steering, and the system currently supports frequency ranges at KU, K, KA band, W band, and all the way up to some millimeter wave frequencies up to 60 to 90 gigahertz. The design is flexible with the RF interfaces. We're supporting open architecture, VPX, and government open architecture standards. You can see in this schedule the current completion of the phase 1 option of the SBIR contracts. Additional funding on the DARWIN program has been provided through a Navy RIF program, which we are calling the phase 2. In that phase 2 program, we further developed the W-band hardware, and along with a partnership with Pacific Antenna Systems and some interfacing with some of the pod demos that are supported by the George Mason University. We have some options in our contract to continue with within the Navy R&D community to further develop this technology and implement it on airborne pod systems that are currently in the inventory or planned for future systems, such as a new pod for communications on the F-18. And we can see this technology, various subsets or as part of a complete system, being part of a future pod demonstration program for the Navy or other services. So DARWIN as a system architecture for a reconfigurable software payload. We're basing the design on a platform under multiple projects within the Air Force, Navy, and DARPA funding. It's designed for high-flying airborne modem applications for DARWIN, and the program with more stringent environmental and swap constraints than this program, where the lack of air heat exchange makes for very challenging thermal cooling requirements. We're using mill standard components that are COTS off the shelf, including the OpenVPX cards and chassis, which are modeled after SOSA. All the modem digital beamforming, the I/O, including MIP-based and SMTP controls, the gigabit Ethernet and VITA49 functions are already up and running on the current DARWIN platform. prototypes, and they're being transitioned to some VPX airworthy chassis hardware from the 19-inch rack sizes. Again, we support 16 channels capable of 1 gigabit throughput each simultaneously. We can support up to 16 simultaneous independent apertures, including any discovery, pointing, acquisition, and tracking functions that are needed. We can simultaneously divide up into carriers at different bandwidths if needed. We have fixed physical mapping of the network interfaces to apertures, and we offer up to 2 gigahertz of instantaneous transmit and receive bandwidth. We can support direct analog connections via RF connectors to legacy radios to add waveforms agnostic. Digital beamforming provides anti-jam, AI beam, no steering to legacy waveforms and radios. It's a very powerful processing platform. It can handle discovery, pointing, acquisition, and tracking for directional comms. And we're fully demonstrated and aligned with SOSA and OpenVPX standards. Again, we're waveform agnostic and modular platform, so we can integrate new waveforms as required by customer or branch of the service. We offer various antenna interfaces, either analog or signal conditioned up converted to bands where the direct digital synthesis is not available, including direct digital and analog interfaces to electronically steerable phased arrays or tracking gimbal microwave dish antennas. We offer direct connection to modular COTS RFPAs and a MaXentric high efficiency GaN-based envelope tracking digital RF SSPA if needed. So MaXentric is targeting a transition to fleet of this as a communications package to PMA-266, where they might need networking and directional waveforms in future programs for range extension, better spectral efficiency, and if they need in the future LPI, LPD, anti-jam capabilities, this platform offers the ability to integrate those capabilities through software and existing hardware configurations. The array topology offers affordable multi-beam capability for airborne nodes that can be supported at a number of frequencies for both line of sight and beyond line of sight capability to the surface fleet and to airborne platforms. It can also be configured as a radar system or electronic warfare capability or combination of EW, ISR, and communication waveforms running simultaneously on the platform. And we can support both FDMA and TDMA waveforms as well as commercial standards in the 5G bands that might need a QAM or OFDM waveform interoperability with cell phone towers and systems in the future. From a market analysis standpoint, phased arrays and software-defined radios and millimeter wave data link systems continue to shrink in size with increased performance. MaXentric's modem and the ESAs through digital beamforming and combining offer significant advantages to radar and communication application, and our market segments in those areas continue to grow within the company. MaXentric has developed the software-defined radios and digital beamforming arrays for both radar and communication markets, and we spoke both DoD and commercial customers. Distributed multi-beam AESA systems can provide higher RF to DC power, combining efficiencies over a single amplifier and legacy fixed position antenna systems, and this can offer significant advantages in reducing the size, weight, and power, and ultimately the cost of deployed system. And we can support rapid development of these systems because we have a design that has open interface standards and platforms that are commercially available. And we're very capable of providing you with prototypes and something to sample in a short amount of time. MaXentric has identified dual-use applications for this technology, such as commercial air-to-ground systems for high-bandwidth Wi-Fi, DoD next-generation BE-CDL system, extension of this technology for higher bandwidths, and we can include millimeter wave and covert communications as an example. The system could be used in a commercial sense as sort of emergency communication system, maybe when a hurricane or otherwise the communication network has been flooded out and you need a backup for emergency rescue. The MaXentric Technologies in both the digital beamforming SaberMax and the DARWIN system is modular, and we can scale this to larger or smaller aperture sizes and different frequency depending on what sort of ranges you're looking for and what are your limitations on your size, weight, and power of your airborne platforms. The DARWIN approach integrates into a multifunction pod-based systems as an auxiliary payload, but if the apertures need to be integrated conformally on a platform, we can customize this integration for the particular requirements. The sizing that we've accomplished for the air-cooled airborne packages is based on standard pod designs that are commonly used on existing aircraft, which will allow for rapid integration and test capability. And in terms of a partner, MaXentric provides RF and the digital interfaces, and we have the flexibility of hosting different vendor modems or software on our current VPX chassis and platform. As a wrap-up, MaXentric Technologies, Brian Choi is the lead system engineer. He's a senior communication system engineer in our Fort Lee, New Jersey office. His contact information is shown. If you have any questions about the current hardware or software development, please contact Brian. And if you have any questions about future business development or questions about other applications, please give me a call. And I want to thank you for your time today. MaXentric Technologies is well positioned to continue to grow in the niche markets of wideband amplifiers, custom ICs, software-defined radios, and advanced RF systems, supporting both commercial and government sectors. So thank you again for your time today, and talk to you soon.